we talk about antennas in this course because antennas are the easiest way for us to visualize in our macro world electrons moving up and down a conductor, okay? And in reality, most of the light that we perceive, or the visible light that we perceive, is emitted by atoms in things. If I heat up that metal wire enough, so in this situation, in the macro world, what I'm doing is I have a frequency generator. Well, this one is a receiving antenna, isn't it? But imagine this is a transmitting antenna, and I have a frequency generator attached to it, which causes the electrons to vibrate between the two poles, backwards and forwards, and backwards and forwards. In reality, most of the time, the visible light that we experience, the one that we have the most experience with, is caused by heating up this piece of metal. If we heat it up enough, it will start to glow, start to emit its own light. How does it emit its own light if I haven't got a radio frequency generator causing these electrons to move up and down it? Well, light that we see has very, very short wavelengths compared to this radiation, which is radio waves, which we've been describing with regard to the antennas. The very, very small wavelengths, and I'm talking about nanometer wavelengths, hundreds of nanometer wavelengths, which we perceive as visible light, are caused by oscillating electrons or oscillating charges that make up the metal. And the charges are bound to atoms, or not bound to atoms, but they move around atoms. These little atoms vibrate up and down and cause light in the region of hundreds of nanometers. And that we perceive as visible light. I hope that's reasonably clear. We will go into that a little bit more later. So, but for simplicity's sake, we talk about this idea of antennas. And here we have, from last lesson, we have a city antenna, which is this is a receiving antenna, and we have a radio attached to it. And what happens is the light comes in, the electromagnetic field comes in. So we have an electric field and a magnetic field at right angles to it, and the direction of propagation of that wave is at right angles to both the electric field and the magnetic field. But it's the electric field that causes these electrons to oscillate backwards and forwards at the same frequency, at exactly the same frequency as this oscillating electric field, therefore transmitting a signal to the radio, which can read that signal and turn it into sound waves via a speaker. Okay. Yeah, it's not that complicated, but it's probably a mouthful what I just said, I suppose, isn't it? Okay. So the last thing that we said was transmitting the signal. We think of each of the metal rods as one half of a dipole. So these aren't connected. That's not one metal rod. That's two metal rods. One that way and another one that way. And if I have something connected to it, a potential difference connected to it, I can cause those electrons to oscillate between the two. Okay? Okay. Two different halves, yep. Oh, because if I connect a radio frequency generator to that, so let me get a good color here. I connect something there and I connect something to the other side. And what we call the image is that. Why do you think I draw this squiggly line as the radio frequency generator? Yeah, it's like it's an alternating current. Yeah, so radio frequency generator, generator. And what that does is it causes this to be positive and this side to be negative. What will that do to the electrons? The electrons will all race up to this end, won't they, on this side? Okay? And if I flip it around again, make it negative and this positive, the electrons will all race over to that side. Sorry, they'll all go to this side, won't they? Sorry, I had it the wrong way around. But the electrons will race whichever end that they want to as I change the polarity of these two wires, these two sides of the dipole. Okay? And by causing them to move to either side, they're oscillating. If I cause this thing to have regular oscillation, then they're going to oscillate with regular motion and create an electric field. All right. Remember that the amplitude of the acceleration, or the magnitude of the acceleration of these particles determines how big or what the magnitude of the electric field that is created is. All right, and I'll show you that applet again. Just give me a second here. Radio waves. So remember, I can cause this thing to oscillate, and what these vectors are here, these vectors are the acceleration that that electron is experiencing. Can you see how at the bottom of its path, its acceleration is at a maximum in the opposite direction? At the top of its path, its acceleration is at a maximum in the opposite direction. All right. If yes, question. Right. Why is it dampening? You mean? Why is it getting smaller? By moving through the air, this medium which is air, it does, even light gets dampened by having to oscillate the particles as it moves through it. It loses energy to the atmosphere. And so what we have here is oscillation of the electrons with smaller amplitude, but exactly the same signal because it's the same frequency of light. It's exactly the same frequency, it's just a different amplitude. And so what this radio station has to do is has to say, okay, what is the necessary amplitude that we create here such that at this house at this distance far away can receive our signal with strong enough amplitude that their radio can perceive it as a proper signal without static. Okay. If I draw, no, what do I want to draw? Oh, the electric field. So notice though, forget about the red line now. Just have a look at the electric field that's created. What's different to the acceleration that we were looking at earlier? Yeah, the acceleration was in the opposite direction, wasn't it? The electric field, however, is propagated in exactly the same direction as the oscillating charge. All right. So look, the electric field is at a maximum where on the same side as the charge is. All right. So the electric field oscillates with the charged particles. And the acceleration of that charged particle is opposite its direction. Yes. Yeah, so the signal, if you know that light travels at light speed, all of these waves that we describe in this topic travel at light speed. So this is, we wouldn't be able to see this, of course. This is traveling really slowly compared to light speed. The beauty of light speed is that it's so fast that I can send one frequency this fraction of a second, and the next fraction of a second I can send a different frequency. And those changes in frequency determine a signal that this radio can perceive as, or we can perceive as music or TV or whatever it may be. Oh, okay, yes, okay, that sounds reasonable. So amplitude modulation uses the amplitude for the signal, and frequency modulation uses frequency for the signal. Yeah. Okay, so what if this was an AM radio station, you'd see this oscillating charge actually has different amplitudes at different times. Split seconds, very short amounts of time, and this radio station, if it was FM, has the same amplitude all the time, except the frequency changes. Okay, thank you for that. Yes. Electric fields, yeah, with regular oscillation, yes, they form waves. Sorry, I don't understand. Oh, the other mode, yep. The electric field, yep. Oh, no. What this is here, I don't know why they show this. This is the amplitude of the acceleration that the particle experiences. And in fact, the electric field is this one, is this green one here, okay? This one here is just the acceleration or the force that the electron experiences. And I don't know why they've got it continuing along here. They shouldn't do that, I don't think. It's a good point. If you think about it, how is it that if I look at the acceleration, so the question is, why does the acceleration go opposite? There's the force on the electron. How do I get an electron? There's no pause in this program, is there? Oh, yeah, there is. Sorry, right at the bottom. Yeah, that's right. Look, as the electrons or the charge here is reaching the top of its path, the force is in the opposite direction to get it to come back in the opposite direction. As it reaches the bottom of its path, the force is in the opposite direction, trying to change its acceleration in this direction. And so if the force is in this direction, the acceleration is also in that direction. I hope that's clear. Okay. Let's move on. If you were to, oh, actually, I'm going to have to get our notes. If you were to look at this wave coming towards you, this is what you'd see. So we've been looking at the waves in profile. So we've looked at the side. So here's the oscillating particles here. We've got an oscillating electric field in the same direction as the oscillating particles and the magnetic field at right angles to it. Okay. If we were to have a look at the electromagnetic field coming toward us, this is what we would see. Is it there? Yes. Okay. Remember the diagram that we were talking about before, where we had 3 points on a conductor A, B, and C. A was where the acceleration was what? Yeah, that's right. Right in the middle of the conductor part. At B was where the acceleration was 0 and the velocity was at maximum. What point is this here? I'm only interested in the electric field. Remember, the electric field oscillates with that charged particle. The electric field has magnitude maximum where the acceleration is a maximum for that charged particle. What point is this here? Which one? It's a crest for the electric field, yes. When we were talking about this diagram earlier, A, B, and C, which point is this here? It's A or C, isn't it? So this is A or C. Remember, this is each of these images is how we would see the light wave as it comes directly towards us. Okay, this is the next moment in time is each of these pictures. Next moment, next moment, next moment, next moment. This point here, where the electric field is at a maximum, is where the acceleration is at a maximum at A or C. What's this point here? Yeah, that's B, isn't it? Where the acceleration is 0, therefore the electric field is 0. We come back here, this would be, yeah, so if this was A, then this would be C, wouldn't it? And this would be B, and this, of course, would be A again. Okay. Oh dear, I've written all over the top of that. That doesn't matter, I suppose. this diagram shows the EM field traveling toward us, just to give you an idea of the perspective. Okay, so an acceleration maximum here. This concept of the oscillating electric charges is probably the most difficult part of this chapter 9, topic 9. If you can understand that, you'll understand everything. It's probably why I go on and on about it and show it in different ways. Here is another situation. Here we have a radio frequency generator, and if you have a look at this point here, we have all of the negative charges here and all the positive charges here, and this is where right at the moment where the charges here, and they're saying that the charges are in the direction, go in the same direction as the electrons. So these might be little electrons up here. The electric field is at a maximum at this point, where their acceleration is at a maximum. If we come to the next moment, here, the RF generator is basically generating no potential difference. The charges are balanced here and balanced here. We have no electric field being created, okay? It's where the acceleration of these charges is equal to 0. Essentially, that, if you thought about it as one electron, it would be at this position here. In the next moment here, we've pushed all of the electrons down to this end, and their acceleration is at a maximum in the opposite direction. And so the magnitude of the electric field at that point is at a maximum again. And they start to draw the wave here. So each of these is a moment in time. Look, the acceleration is 0 again, so is the electric field. The acceleration is maximum again, so is the electric field. And then all those points in between, all of these points in between, are points at which the acceleration is not at a maximum and not at a minimum. All right? Can I move up here? Is that all right? I'll explain that in words here. So here, and I'll talk about it here too. Dylan. I hope that's reasonably clear. This oscillation, or the wave that we see, is the electric field strength. The oscillation is transverse. How would you describe a transverse wave? Yes, that's right. So oscillates at 90 degrees to the direction of propagation. Of the wave. Important also, we say that the wave can be polarized. The plane of polarization, plane of the oscillation is defined by the plane that the electric field resides in. So whenever we're talking about this electromagnetic radiation and we're describing it, we always describe these things as firstly an electric field and then a magnetic field. We say the electric field first because the electric field is the one that's created by the oscillating charge. The magnetic field is the one that results. Did I show you the MIT demonstration the other day? Oh, okay. I should have just, didn't I? Radio frequency transmitter. There's the transmitting antenna. That's a dipole, two halves there. Here's a receiving antenna. There's a light bulb on that receiving antenna. They're not connected in any way. It's just the oscillation of charges creating an electromagnetic field that you can't see because it's radio frequency, which causes oscillation of charges in that receiving antenna. The oscillation of charges, the light bulb perceives as a current, and so lights up. Yeah, you still receive some signal. That's right. Weaker. You'll notice that it was weaker the further from parallel that you were. Yeah, yeah. So yeah, well, if you think about the oscillating charges, the charges are oscillating in this transmitting antenna like this, much faster, of course, back and forth, back and forth, back and forth. They're creating an electric field that goes out like this. If they were creating an electric field that was going out vertically, polarized vertically, then all it would cause in this receiving antenna is oscillation of the charges right at this moment here, one little moment in the whole antenna, one little space, up and down, which is no current across that light bulb. Whereas because they're moving out horizontally and causing maximum oscillation of the charges when the two antennae are parallel, maximum oscillation when they're parallel, we have maximum acceleration, we have maximum current at that point. When it's vertical, when he orientates the receiving antenna, see how almost vertical, we're still getting some signal, but not much. When it's perfectly vertical, there is no signal. All that's happening is this oscillation is coming out and striking, you could think of it as striking one point there, perhaps, and causing oscillation of charges at that little point there, which is no current. All right. Can I move on to the next page? Is anybody still wanting? Yes. Sorry, I don't understand. Yes. It does. You mean by oscillating charges it creates light? Yeah. The oscillations though, like I said before, the oscillations by that transmitting antenna that we saw before are quite long and slow. Okay, so low frequency, big wavelength. Okay, I'll go back to that video just to refer to it. Low frequency, big wavelength. Okay, and if you look at the filaments in those light bulbs, really compared, really small wavelength, but much higher frequency compared. And that small wavelength is of the order of 4 by 10 to the minus 7 to 7.5 by 10 to the minus 7 meters, and we'll talk about that shortly. The wavelengths are much smaller, hence the frequency can be much higher, and it turns out that specific wavelengths and frequencies our eyes are sensitive to, and we see it as white light. White light because they're not oscillating at the same time. They're not oscillating in the same time with the same frequency. All of those charges that make up that filament are oscillating at different rates, and so we see all the colours of the rainbow, which means we perceive it as white light. Mm. Oh yeah, no, it doesn't, because you can imagine that those oscillating charges. Yeah, I'm saying that the electric field comes out like this in exactly the same plane, but in fact, if you were to orientate it, make this thing fall over, and those waves would still be coming out. They'd actually be coming out this way as well, in all directions, in 360 degrees. I beg pardon? Like a circle around it, yeah. So I'm only ever talking in 2 dimensions, which isn't true, because they go in all directions. Yeah. Yeah, Yeah, it's probably more difficult to picture than just 2 dimensions. Yeah, that's all. Yeah, it's like a cylinder. Yeah, that's right. If you picked one moment, you'd have a cylinder of waves. So, well, the waves would be in a plane of a cylinder. Yeah, that's right. Yeah, and so it doesn't matter if he's standing here or if he was standing up here. Okay. Back to here. You guys don't have to, at this level, don't have to worry about 3 dimensions so much. You just have to know that it exists. Here, I'm going to call this my transmitting antenna. And this is my receiving antenna. The oscillation of the charge particles, in this case electrons, is going to be up and down this transmitting antenna. And the wave that results will look something like this. Okay. Of course, there's a magnetic oscillation as well, but I'm not going to draw that in here. That will just confuse the diagram, I think. The signal here is strongest when the two antennae lie in the same plane, and that might be anywhere. So they orientated parallel to each other, you could say, is probably a better way to say it. I could rotate that antenna all the way around and I would still receive the strongest signal. All right? As long as I didn't orientate it vertically or any variation in between. So the signal is strongest What's that, Josh? Yeah, you could say if they're parallel to each other. Yeah, that's right. Or parallel. Yes. You can see here, I'm going to draw another diagram. It's the same diagram, except I'm going to orient the receiving antenna vertically. There. Let's have a look at that electric field. You can see, and I might start it here this time. It doesn't. You can see how all this electric field is going to do, and this is E, I better label that, E, electric field. All this electric field is going to do is cause the electrons to oscillate in that little point there, backwards and forwards. And that is not going to create a signal in this antenna. There's a new type of antenna though, which is the digital antennas, and I think they transmit much smaller wavelengths. I'm not sure about this, but they're not the big antenna that you're used to seeing on people's roofs. They're quite a small small unit, and so they must have very, very small oscillations to be able to pick up that signal. Small wavelength, higher frequency would denote higher frequency. With this orientation, charges in the receiving antenna will not oscillate in the plane of polarization of the electric field. At what speed do these travel? Yeah. Speed of the wave in all cases is c, which is equal to 3, it looks like 3.6, I'll just say 3, by 10 to the power of 8 meters per second. 300,000 kilometers per second. Yeah, 300,000 kilometers every second. Here to the moon in 1.3 seconds. Round the world 7 times in 1 second. Here to the sun in 8 minutes. 8.8 minutes, I think it is. It's a fair way away, and it's 150 million kilometers. And to the nearest star, the next closest star system to us is 4.3 years at that speed. C is equal to F lambda. That's what we're going to use now. We used to use V equals F lambda. But in this case, it's always going to be C if we're talking about light. Okay. I have a question for you. A ray of green light has a wavelength of 540, what is that? Nanometers in a vacuum. Find its frequency. And a radio station broadcasts with a frequency of 720 kilohertz. Find its wavelength. Have a go at those, please. Lambda is equal to 540 times 10 to the minus 9 meters, or 5.40 by 10 to the minus 7 meters. find its frequency. So C is equal to F lambda. F is equal to C on lambda, which is equal to 3 by 10 to the 8 meters per second on 5.4 times 10 to the minus 7, which equals 5.56 by 10 to the 14. Hertz. 2. Radio station broadcasts the frequency F equals 720,000 hertz. C equals F lambda. That's the formula I'm going to use, but lambda is equal to C on F. 3 by 10 to the 8 meters per second divided by 720,000 hertz. 4.17 by 10 to the 2 meters. Which is about 417 meters. Radio waves can have massive wavelengths. That's why they don't hurt us, because they can't oscillate the molecules that make us up very well, very quickly. They can't oscillate them, they can't damage them. Any questions there? Okay. Last thing that you need to know for this topic is Roy G. Biv. This is just visible spectrum. We have these. We're sensitive to this visible spectrum, and so we're used to thinking that this is a large portion of the electromagnetic spectrum when in fact it's a very small portion. There's a video that I'll show you afterwards which shows just how small it is. I think if you look at a distance of about 2,500 miles, which is about, I think it's about 4,000 kilometers, the distance that the visible spectrum is only that big in that distance. Okay, so the visible spectrum is very small, just under 10 centimeters at that scale. Apparently, I haven't done the calculation myself, but apparently that's the size. What we have here, what you're seeing is just, this is non-visible infrared, which is just heat, and this is ultraviolet, also not visible. In between, we have red, orange, yellow, green, blue, and violet. You'll notice that as we go from violet through to red and infrared, we have a longer wavelength. And as we go from red through to violet, we have a higher frequency. So higher wavelength, higher frequency. They're inversely proportional to each other. The longer the wavelength, the lower the frequency. And we might have mentioned before that physicists like to talk in terms of frequency when they talk about light, because energy is directly proportional to the frequency. So if they say a high frequency, they mean a high energy. We do talk in wavelengths, but not as much. When we're talking about colors, we talk about wavelengths. The electromagnetic spectrum is the next picture I'll show you. We might have to get... This is the entire spectrum. This diagram, obviously, from what I said before, is not to scale. What we have here, you'll notice that radio waves down here, then overlapping them, we go into microwaves, and overlapping them, infrared. Visible light, there is no overlap. Visible light is visible light. It's what we perceive as visible light. Ultraviolet overlaps X-rays, overlaps gamma rays, overlaps cosmic rays. You know the origins of most of these things. We did talk about them before. And notice that as we go this way, what's increasing? Frequency increasing? And so if that's the case, then wavelength is decreasing. Yes. Yes. Well, remember what microwaves are, though. They're just the name that we give to those waves that have a wavelength that is approximately at the micro region. And so you might find that some scientists somewhere would say that microwaves tend to also emit, or they tend to also be, we perceive them as infrared radiation, which is heat. Okay, so these areas here are grey. They're just names for areas of the electromagnetic spectrum that we've given, and usually has something to do with how we perceive them. So infrared we perceive as heat, but microwaves in the micro region region of the spectrum 10 to the, what is that, 10 to the, I can't read that, 10 to the 2, 10 to the 4, 1 meter there. Oh yeah, 1 meter, 1 centimeter. So microwaves are around the 1 meter to 1 millimeter mark here. Infrared overlaps that by the looks of things here by this diagram. You might find that in different labs, in different physics textbooks, that these overlaps are completely different, I would say. I think this is a grey area here. Same here and here. There's some wavelengths that you do need to know. And I'll copy them and paste them here. For the purpose of this course, you need to know the following approximate wavelength ranges. There have been questions. If you remember these, it's likely that you'll gain a mark in the exam, because you'll be able to say, once you do a calculation and the question says, in what region of the spectrum is that, you'll be able to say. The application to this topic is the LADS, Laser Airborne Depth Sounder. Yes, LADS. So this is Laser Airborne Depth Sounder. It's an acronym. LADS is an acronym for Laser Airborne Depth Sounder. Uses an aircraft flying over water to record the depth of the water by sending laser beams and reflecting them off the water surface and the bottom of the sea or ocean. So here, this aircraft is sending down a laser beam. One of them is being reflected back off of the surface. The other one is being reflected off of the ocean floor. And if we record the time difference between the two, receiving the two laser beams, and we know the speed of light, the speed of that laser light in this water, in this salt water, then we can determine the depth of that water. Yeah, it does. They do. They would say that through air it's very close to the speed of light. Yeah, that's right. Well, yeah, I'll talk about that. So yeah, the idea that fish get blinded by the light, maybe. Yeah, poor fish.